All right, so today we're going to talk about area and arc length and polar coordinates. So the concept is actually very simple, right? This is the area of a sector right here, where if you notice pi r squared is the area of a circle, and this little part right here is just the fraction of the circle that's being shaded right now. Okay, so when you do the math, you get this formula, right? Now on this one right here, say that I'm trying to find the area of this polar graph. Okay, what I would do, just like I did in calculus one, all right, what we do for to find the area under the curve is we make a bunch of rectangles that are infinitely thin. And when you add those up back to back, right, it gives you the exact area under the curve. Now, this is very similar, except for instead of having rectangles, right, we have, if you will, little slices of pie that when you stack one on top of the other, right? If you add all these little slices right here, if you add up all the areas of the slices, right, and using this formula, then you would get the exact area under the curve. Now, I know this is pretty new to you, so remember that when you have this r is normally given to you by some function that takes radians, or excuse me, an angle in radians as your input. Okay, so then again, basically it's doing what I'm saying. If you add up all the little slices of the pie, then you're essentially integrating, all right, from angle alpha to angle beta of a function that takes theta as its input, which is r. So this is the formula. Long story short, this is the formula we're going to use for the first half of this notes. All right. At first, this is actually not too bad, all right, especially when it comes to a shape like this. Now, just a reminder of how we could quickly graph this, right? But don't forget that all of these come in when you plug in, for example, if I plug in let's say 0 for cosine, right? That would give me 2, which is the point that I have right here. So I'll put that in red. So that's the point right there, okay? If I plug in, for example, pi, that would give me -1, and 1 cosine of pi is -1, and 1 minus 1 is 0. So I would get this point also. Okay, and then let's see, if you plug in pi over 2, excuse me, if you plug in pi over 2, that would give you this point. Okay. And then by doing that, all right, around basically, the more angles you plug in, you start finding out all the different points on this graph, essentially. All right, so you start finding every single point until you create that shape. So that's how that function works. But remember how we found it? The trick that I show you in the last notes was basically this, right? That if you have, let's see if I remember, if this is a, you had like a plus b cosine, essentially. All right. And if a divided by b is 1, okay, then this is basically, well, actually, this is a right here. This is your a's. Again, if you have a 1, basically is going to create this shape. I call it the heart shape, if you will. And then after that, for example, how do you get this point? You basically subtract a minus b, which in this case is 0. And this point right here would be a plus b. But remember, that's just really a trick to remember how we found this. But essentially, all we're doing, the real way to do it is you plug in values for theta, right? And that gives you the shape of that graph. So anywho, so now we're going to use that formula that we have here. Remember, the area is equal to 1/2 r squared. Now, it turns out that sometimes the hardest part is just finding this, the definite integral. Like, this part is not very hard for me to write, but to write the rest, and this one's not too bad, I can go from 0 to 2 pi. Okay, it goes all the way around the circle. And so this one's not too bad. You can do it like that. You could actually have different values right there. It would still work. But essentially, that's how it's done. Now, I'm going to quickly go to let's see, how far did I get on this? Okay. Yeah, let's quickly talk about how I would do this without a calculator. Okay, so I would go ahead and square that function, which means I'm going to have to FOIL it. And I would get 1 plus 2 cosine 2 cosine theta plus cosine squared. D theta, right? So I'm taking the integral of all this. And then now, a trick that you can use all the time, right? Especially if the only thing that's going to give me trouble here to integrate is the cosine square, all right? I don't have just a straight up antiderivative of that unless I use a double angle identity, right? So that's basically what I go to. If all I have to do is take the integral of sine square or cosine square, then I go immediately to the double angle identities here. And this is the double angle identity. If you integrate all of this, you get theta plus 2 sine theta. Again, that was not the problem. All right, plus this would have been 1/2 right here. Okay, so if I integrate that, I basically get theta over 2 or 1/2 theta, whichever one you want to use. And then now I have to integrate 1/2 cosine of 2 theta. Remember cosine of 2 theta? Think about it. Okay, 2 theta would be u, du would be 2. I don't need that 2. I would divide. So we get a 4 down here. Right, again, if you are interested in knowing how to do that, or if I lost you at some point, please let me know when I see you in class. All right, now I'm going to start plugging in everything that I have here. So I have 1/2 of 2 theta plus 2 sine of 2 theta, and that's going to be 0. Plus plus pi. I keep saying theta. My apologies. I just realized I said that like 50 times. Sine of 4 pi. All of that over 4. And if I plug in a 0 into every one of these, I will get 0 for everything. So I don't have to do at least that part. Now again, remember that sine of 2 pi is 0. And sine of 4 pi is also 0. Right? So if you just add the like terms, and I think I forgot let's see, I think I forgot a pi over 2 here. Yep. Let me check my other notes. Let's see. Nope, that is 2 pi over. Take that back. That was good. All right, so that's going to be 3 pi over 2, or 1/2 times 3 pi, which is 3 pi over 2. All right, so that's that for that. All right, let's go ahead and move on now. This is when things take an interesting turn, if you will. All right, so in this case, okay, the easiest thing to do is for you to find the area, because it wants to know the area of one petal, right? And that's actually what we want, because it gets really complicated, or it doesn't get complicated, it gets confusing at some point. You'll see. Okay, so what we're gonna do here first is we're gonna find our polar zeros. All right, and our polar zeros are very important because that's going to basically tell us where integration limits are going to be. So we're going to set, to find our polar zeros, we have to set our function equal to 0 and basically solve, right? So this is sine of 3 theta is equal to 0, which is going to give me, see, where is sine equal to 0? Well, it's equal to 0 at 0 and pi, right? Right, if I divide both sides by 3 on this side, I get 0 still. This one is going to be pi over 3. Right, so essentially what I just found, okay, let's see, pi over 3 would be right there. This is my pi over 3. And this right here would be my 0. Okay. So after that, really, all I would have to do is those are my integration limits in this case. I don't know if that's the right term to use, but let's just go with it. Remember, it's 1/2 r squared, right? R in this case is 4 sine of 3 theta squared, like that, d theta. All right, and again, let's see what we got here. Again, this is not the only way to do it. I've just mentioned this, right? If I square this, I would get 16 sine square of 3 theta. That 16 can come out, and I can make this an 8. So essentially, what I have to do is take the antiderivative of sine square of 3 theta. Now, I just said this earlier, but if you don't remember, anytime I have a sine or a cosine square, I'm going to use the double angle identity. In this case, my double angle identity for this would be, let's see, 1/2 is 1 minus cosine. That's double this angle. So since it's 3 theta, this is going to be 6 theta. And by the way, this is not a typo. This is definitely cosine, all right? Okay. I can pull the 1/2 all the way out if I choose to, right? Which is going to give me a 4. And put a pi over 6 there. Let's say pi over 3. And then I can take the antiderivative of this now. When I come over here to this side, this is theta. This would be, let's see, the antiderivative of cosine is sine. So this would be sine of 6 theta over 6. And again, if you wanted to, you could, if you want to, basically take the derivative of sine of 6 theta over 6, and you should be back to cosine of 6 theta. This is pi over 3. I'm going to plug all that stuff in. So this would be, let's see, pi over 3 minus the sine of 2 pi. Right? If you plug in a pi over 3, that would give you 6 pi over 3, which is the sine of 2 pi. Now the sine of 2, well, and let me keep going. Finishing a little early here, but if I plug in a 0 there, that's going to give me, if I plug in a 0 for theta and sine of 6 theta, that's going to give me 0. So as you probably already know, this is 0. So my answer is going to be 4 pi over 3. Okay. All right, so this infinite loop thing actually, no pun intended, threw me for a loop because of the way they actually find the limits, right? So it starts off the same. Now remember, if I take the square root, that's going to give me kind of positive and negative square roots of 9 cosine of 2 theta, right? So that's kind of important to note because what ends up happening is that the negative side is going to give you the left side of the infinite loop, and the positive is going to give you the right side, right? But in this case, we're actually only finding the area of one loop, right? So that's all we're interested in. So first, we're going to find our polar zeros again. So that starts off the same. So we have 0 is equal to 9 cosine of 2 theta. So long story short, you get cosine of 2 theta is equal to 0. Right, so I want to know when cosine is equal to 0. So this would be a pi over 2. Okay, and you could also do, and obviously there's more than that, but remember I want to keep this in the positive area. Okay. What would be the other one? Let's see, if it was negative, it would basically all the steps would be about the same. Yeah, all the steps would be about the same, except for at the end, you would get 2 theta is equal to negative pi over 2. And then you can divide both sides by 2, so you get pi over 4. And you also can get negative pi over 4. Okay, so if I put those up here, negative pi over 4 would be, that's kind of not on here, but it'll be about right there. That would be negative pi over 4. And this part right here would be positive pi over 4. That looks terrible. All right, so now my integral will be the following then. 1/2 from negative pi over 4 to positive pi over 4 of this, well, technically r squared is this, so I could write just that. Okay. D theta. And right here, the point is not so much how to find the antiderivative, although we could, all right? But what I'm trying to tell you here is that this is not the only way. All right, for example, if you plug in a 0 for cosine, right, that would give you positive 9, the square root of 9, which is 3. Remember, I'm looking at this. I'm looking at this function, I have to. All right, so that would give me a positive 3. So what I could do from there, all right, assuming I'm only taking the positive here, is I could go from theta equals to 0 to theta is equal to pi over 4 and then double that. All right, a lot of the times doubling an area saved me a lot of time as I went through the homework because I no longer had to think about how this was drawn. Otherwise, I had to figure out, and you're going to see what I'm talking about here in the next problem. Basically, if I'm going from 0 to 2 pi, it's exactly where certain changes happen. So I'll get to that in a second. So let's not worry about that for now. But long story short, to save us time, assuming you can do that, which that one's not that bad at all. All right, the answer should be 9/2. And what I was saying, even though I haven't really checked it, so maybe I shouldn't say this, but what I was saying to you earlier is that you could have twice this function. I'm pretty sure that should give you the same answer, but what do I know? Well, I guess I should know since I'm the teacher, but nonetheless, I think that would give you the same thing. All right, so let's talk about finding the area of the inner loop. Okay, and this is the one that seemed to be not so bad because I really hadn't thought about it as deeply as I should have. And then once I got there, I realized, wow, this can be more complicated for sure. And you'll see what I'm talking about in the homework. Okay, so first, it doesn't matter. We're going to go ahead and start by finding our polar zeros. So we have 2 minus 4 cosine theta is equal to 0. Okay. And then now we're going to solve for that. So we're going to subtract the 2, divide by negative 4, and that's going to give us a 1/2. Now I have to think which angle, right? This is assuming I don't have a calculator, of course. Which angle is cosine equal to 1/2, or a positive 1/2? So we know it's in the first quadrant. And we also know that it's in the fourth quadrant. So you have 2 points that will make this true. Okay. So now the weird part about this, okay, is what I'm about to tell you. So again, let's worry about. So let's see how all this happened. All right. So let me switch that to red since let's keep this consistent here. Let's see. How did I get this number? Well, what happened was, right, when we plug in 0 for cosine, that got me a positive 1, but positive 1 times negative, let's see, that's not even there. Let's see, let me just plug in 0 for cosine, right? So if that's 0, that would give me negative 2, which is this point. Let me see, that is what I wrote. So theta right here is 0. Okay. Now, when I find my polar zeros, what really happened is that that's really telling me, let's see, where it's pi over 3. Pi over 3 would be right here. Right, this pi over 3. So essentially what I'm saying here is that theta is equal to pi over 3. Be right there, and it also gave me a 5 over 3. 5 over 3, let's see. Yes, that's down here. So this is my theta is equal to pi over 3. Excuse me, 5 pi over 3. All right, so when I plug this in, it looks like that gave me 0. So, but what really happened, okay, is that as I did this, all right, what ends up happening is that you have a way where you're going in one loop. So basically, you're going into this loop at pi over 3 and you're coming out at 5 pi over 3. Okay, so there's two ways to do this. I like the following because I thought that it was easier for me to think about. Essentially, what I did here is instead of overthinking all of this, okay, I know that from 0, which remember, I'm basically, let me switch colors here. What I did here is I just try to figure out half of this area, right? So I know that that happened between 0 and pi over 3, okay? So what I did myself to avoid some, and again, this is not the only way to do it. This is just what I found to be easier for me, is that I double that area, right? So remember the 2 just came from me doubling an area. The 1/2 is from the formula. And then I can go from 0 to pi over 3 of 2 over 4 cosine theta squared d theta. So again, and let me check that on my calculator real quick. You can kind of fast forward if you like, but I'm pretty sure I did this earlier. All right, let's check this out. And by the way, if you're going to plug this in the calculator, I would highly recommend, especially as this stuff, yeah, that is the right answer. As this stuff gets more complicated, when you're going to plug this in your TI-84, assuming that's what you're using, please go to y equal, plug in that function. Okay, put that as y1, and then use your alpha trace button to just kind of put that into the integral formula. But anyway, so yeah, this does work out. I'll show you also what they put, which I honestly don't like. I think that's, at least for me, that was more confusing. Let's see. They said you could have done also. You could have done this. So this is other answers from negative pi over 3. So all these are going to get you the same answer. It's just for me, doubling the area just basically made it where I don't have to think about all these angles all the time, because that to me was very confusing. So anyways, you could do this and you don't have to double anything. You can kind of see that, I guess, but I don't like it. You could have done that, and also they also did this one. Well, they gave me an example of this one, I should say. They did this from 5 pi over 3 to 7 pi over 3. And again, I invite you for yourself to make sense of this. And I'm just going to write r squared because I don't feel like rewriting the whole thing. Woo. All right, so you could have done those two and they all got you this same answer. All right, so let's move on now. Let's see. Let's go to the next one now. The shape on this one at least is easier. All right, so what we're trying to find, and this is always the important part, is we're trying to find the area. This is the lies inside the circle. R is equal to 3 sine, right? And outside the cardioid, I think I'm saying that correctly. So basically what we're looking for is this area right here. Okay. So really, you really need to sit down and figure out how to find that, because at first, my brain does not work in polar coordinates a lot of the time, so I did have to sit there and think about it. But nonetheless, right, we don't need necessarily the polar zeros on this one. We really don't need them. But what we can do instead is we need to find this intersection points. They're located right here. So I need to figure out these intersection points. Right, so to do that, I will set the two equations equal to each other. So I have 3 sine, let's see, 1 plus sine theta is equal to 3 sine theta. And then I solve, so I have 2 sine is equal to 1. Man, writing theta on this screen, it's hard. Okay. So now I'm trying to figure out when sine is equal to a positive 1/2. All right, so we know this happens in quadrants 1 and 2. So this is pi over 6 and 5 pi over 6. Okay. So that's that for that. And then basically you need to think about what's going on, right? You're going to subtract two different areas. So again, you're going to subtract two different areas. So what I'm going to do first is I want to find the area of the entire circle. Okay. And by the entire circle, I actually mean from here, right? So it's actually going to start from that point and end up at this point. So from, I'm going to write it like that. Let me write it like this instead. So from, this is 5 pi over 6. And this is from pi over 6. Okay, so essentially, remember, you have a bunch of little pieces of pie. They're only going to, so all you're going to find is this kind of strange area that does not cover the bottom part. So what you're not going to find, well, actually, man, I got to think about this for a second. Okay. That circle from pi over 6. That's almost going to give you the entire circle, but not quite, I think. Let's see. Okay. So we have 1/2. And we're going to go from pi over 6 to 5 pi over 6. And actually, I think for the circle, that's basically going to give you almost everything. Let me think. There's something that's not going to be given to you if you go between those two. Yeah, you're going to be missing a little bit of that circle, but that's where you want to find the intersections at that point. So we're going to have the area of the circle. And then we're going to subtract the area of the cardioid. Right, to find that area, I have to do this and square it, right? And when you do that, you get pi. All right, so again, the ones with intersections, it makes it, in essence, a little bit easier because you don't have to overthink basically these values right here. Whoops, these values. You don't have to overthink those. All right, so let's go ahead and move on. Right. So I actually find the arc length and the arc length to find the arc length of a polar curve is a lot easier than what we've been doing because it's pretty straightforward. All right. So again, we had a formula that looks like this, right? Except for last time, I think we had dx over dt, but it's the same formula as we had for the arc length earlier. The only difference is that dx and dy vary according to theta. Now, we have, if something is in polar coordinates, this is always going to be easier. All right. So always do it like that. You could do it this way. It's not impossible, but I found that to be just more math for no reason, really, because it's going to give you the same answer. So let's go to example 6. Okay. Example 6. Okay. So again, you could do it. What? Okay. We want to find the arc length of the cardioid. So we can, if you want to do it this way, you can. Hold on, let me do it. I'm going to write it out. See if you want to write this, but I just want to show you that it does give you the same thing. So feel free to fast forward if you want to. Remember, that's just this right here is just a formula that we should already know. I'm going to plug in 1 plus sine for r. And after I distribute this, then I'm going to take the derivative. And on this one, when it's just a cardioid, there's no thinking involved. You don't have to think about any loops or anything like that. Let's see. Now I'm going to do the y coordinate. Let me zoom in. Having trouble writing this. Oh man, I'm stupid. I meant to write a sine there, not a cosine. My computer's slightly lagging too, which makes all of this a little bit more interesting. So then dy d theta. This is a little bit easier derivative. I have a chain rule here. Now again, the arc length will be between 0 and 2 pi. Remember, I'm using the formula that I just showed you. And I'm not going to write all of that again because that would be awful for me. But essentially, you take the derivative and you square it. So a lot of these are going to be done with the calculator, but oh my gosh. Trust me, my handwriting is really not this bad. It's just I'm having trouble writing with this stencil. I don't know what's wrong with the computer here. Okay, so if you put that on your calculator, right, then you get the length is equal to, I believe, 8. Let me check that real fast. Okay. So again, you might want to fast forward through this part. Actually, let me just pause it. I want to make sure this answer is correct. Even though I checked it, I want to just make sure. All right, so let's just pause here for a second. Well, okay, let me pause. Okay, so that does work. It is 8 indeed. Now I will show you how easier it would have been to do it the other way. All right, so I'll just write the other way over here in a different color. Here, all you would have to do is find the derivative of r, which is cosine. And this would be the integral from 0 to 2 pi of the square root of r squared plus r prime squared d theta. Again, if you put that on your calculator, I promise you get the same thing and it's a lot faster. So let's go on to example number 7. Okay, so in example number 7, all right, we're going to do the same thing. We're going to find the arc length. Let's see. Is this the last example? No, there's one more. Okay. So in this one, we're going to go between 0 and 2 pi, and we're going to go ahead and do it with this formula right here. R squared plus dr d theta squared d theta. All right, so that's the formula we're going to use. So then dr d theta is equal to 2 sine let's see, the antiderivative of sine. Yeah. Okay, sorry. The derivative of cosine is negative sine. Okay, so now all we're gonna do here is just plug that stuff into our calculator. Again, please don't forget the square root. As I was going through the notes, I actually saw the warning. She actually wrote it on there, the author, and said, do not forget to write the square root in your calculator when you're plugging this in. And I thought, well, who cares? I'm not going to do that. That's stupid. And then I did it twice. Whilst I was doing my homework, I kind of just forgot. All right, so again, please don't forget your square root as you're doing this. Okay, and you can simplify this, and this maybe could be a little bit, this could be solvable is what I'm trying to say, but let's not do that by hand because we don't have to. So this is going to be 16. Okay, and let's go over to example number 8, which is right here. Oh, yeah, there it is. So that one, guys, the same idea. The only hard part about this one is taking the derivative. So this is 1/2 1 plus cosine of 2 theta to the negative 1/2. Remember, I'm using a chain rule here. Times the derivative of cosine of 2 theta, which is negative sine of 2 theta times 2. Right, the 2's are going to cancel. And I'm just going to go ahead and plug this in, right? I'll simplify somewhat, but only because I feel like I have to. Notice that on this one, they actually tell me like where to find my, from what point to one point to find the arc length. All right, so this right here is going to be this squared essentially, which is going to get rid of the square root. I'm just going to put that in parentheses here. And then this right here would be, let's see, negative sine of 2 theta all over the square root of 1 plus cosine of 2 theta, all of that squared d theta. Right? And if you put that on your calculator, you'll get 4.443. All right, so again, guys, the homework, some of it actually was very confusing. Hopefully you're not as confused as I was, but give it a try. All right, and we'll see you next time.